Alright, so we've defined what a derivative is, and we know that it the most simplest notion of a derivative, it's basically describing the slope of a function at a specific point, right? Um, and we sort of covered how you go from a function, right? Uh, and then we use the definitions of a derivative, right? We covered the two different definitions, and we use those definitions to get the another function that describes the derivative. So I'll call this the derivative function. And then we talked about the different notation for it. One of them is f prime if the function is f, right? And so this sort of, yeah, we get it. We have a function and then we're finding its derivative function, which basically describes the slope of the tangent line at specific points on the function f. But given a graph of this function and the graph of its derivative, what sort of relationship is there, right? And this relationship between f and f prime is pretty important because we'll figure out later how we just need one point on this function f, right? Let's say a point x comma y, and then if we're given the derivative function, we can actually get back we can actually use the point plus the derivative function to get function f again. So it's pretty powerful. Right, so let's just start sort of noticing graphical properties of the function f and how it translates to the derivative. All right, so for the starting example, let's say we have a graph of some function that looks like this, right? Now, let me just label this. We'll call this point D. Call this point E. Actually, let me just call this F. We'll call this point F, point E, and then D, C, B, and A. Okay, so this is function f. What can we sort of say about the derivative at these specific points, right? I mean, we're not given the equation for f, so we're just talking about qualitatively and just maybe positive, negative, how much more positive, how much more negative. So the way we can sort of go about this is we can just sort of estimate what the tangent line looks like at each point. So we see at A, if I try to draw a curved tangent to it, it sort of looks like this. So this line to me looks like a big, or big in relatively big positive, right? So I'll just do big plus actually, right? A big positive. Here we see, if I draw a tangent line, it's still positive, but the slope of it is smaller, so smaller, positive. Here, there's something interesting. Our tangent line is completely flat, so it has a slope of 0. And then here we see how we get a negative, and we can call this big negative. And here our slope becomes a little less negative. I think this is a better area to draw a line. So small negative. And then here at point F, our slope becomes 0 again. So we notice how the derivative sort of represents the original curve. Our derivative is initially really big, right? And it's positive, and we see that when that happens, our function is actually even growing at a fast pace. But then as our derivative gets smaller and smaller, our function stops growing as fast, right? You see how this curve starts staggering and slowing, and when it's 0, it just doesn't grow at all. And then once the derivative becomes negative, it starts going down, right? Because our function is not growing anymore, it's actually decreasing. And then similarly, if our derivative becomes less negative, it decreases at a smaller pace, right? And that's because we know that the derivative is basically representing, like, we can say it's the rate of change of a function. So it's a measure of how much the function is changing at a specific value. So at point A, it's changing it's increasing very fast. And because of that, we see after point A, we see how our y value is increasing a lot. At point B, it's increasing, our function is increasing, but at a slower rate. So we start seeing how it takes longer, like a longer interval to grow a smaller amount. And at point C, our rate of change is 0, so it's not growing at all. And at D, it's decreasing at a fast rate, so that's a very small, like changing x is going to lead to a very large negative change in y. And it continues on like that, right? So we see how, in general, how a derivative is sort of describing the rate of change of a function at various points. So what if we have a graph of f prime, right? And we're given an initial value, and we want to find the graph of f, right? So let's say we're given that f of 0 is equal to 0. Let me change the color. Let's say we're given that f of 0 is equal to 0. This is known as our initial value. Right? And then we're given the graph of f prime of x as this. So f prime of x looks like this, the graph. This at point 1, and then this is this. This is the y value here is -1, and then the x value here is 2. So we sort of see here that the derivative is not defined at point 1, right? And recall that when we're talking about the derivative, the definition of the derivative at its core is the limit definition. So here it must mean that the limit of the function f must not exist. There's no or the limit of the definition of the derivative must not exist at that point, because what's happening is we're going as we're going from the positive side to this side, our derivative something else, and from our negative side to this, our derivative something else. And we're also given that so our third piece of information is f is continuous for all x. So let's just start off with the easiest piece of information that we know is that f of 0 is 0, right? So we can just draw this 0, 0, right? And then we know at a positive value, our derivative is constant, and it has a positive value of 2. So that kind of means that at this or starting at 1, that's our case, but at point 0, right? So at point 0, when x is 0, our f prime of 0 is equal to -1. So at this instant, our function is actually decreasing by a rate of -1. So we can sort of try to sketch it out. We know that because the rate of change is constant throughout 0 to 1, it's basically a line that goes like this, right? And then we know that the duration of this is for 1, so we can safely say that the function f decreases from 0, 0 to 1, negative 1. And then starting at x equals 1, our function just starts to increase with the rate of 2. And since this rate of change is constant over time, again, it's a line that we're drawing now. And we basically can draw something like this. And that sort of gives our function. And then this has a slope m equals to like this segment, and then this has a slope of m equal to negative 1. So, I mean, this was an easy sort of example where our rate of changes were constant, or derivatives were constant, and it only shifted once. If we have like a smooth curve that shows like a derivative like this, then we just have to sort of estimate what it looks like here, right? So if we're given that at point 0 or derivative 0, like we know at first our function is growing at a growing rate, so it's something like this, right? And then it starts to slow down its growth, so it looks like this, and it starts to increase the growth again, slow it down, and then increase it again. And what we see here is each time the rate of growth keeps increasing, so it looks more and more steep. But yeah, you just have to estimate what the two graphs will look like, because until you're given equations to work with and other methods, it's basically just qualitatively determining what f looks like from the graph of f prime. So hopefully this sort of gave you guys a idea of what the derivative function really represents and how we can go from the derivative function to the original function, right? I mean, just so we can have like a more clear understanding, maybe let's go from the original function to its derivative, right? So let's say we're given a function that looks like this. It's decreasing, stabilizes, and goes up. Some of this, right? Now let me draw this better. So these are axes, and we have something that have something that looks like this. So it's like a parabola-ish thing. And we'll just call this like negative, or we'll call this 0, okay? So let's call this function f. So we know at point 0, right? Yeah, it's a bit confusing because I sort of drew this here, but we'll call this 0. We know at point 0, our function is sort of decreasing, right? And we notice that as we go from 0 to, let's call this 1, the rate at what it decreases becomes lesser and lesser. And it eventually becomes 0 at point 1, and then it starts increasing again. So that sort of tells me that my derivative at first is like negative, right? And as I go away from 0 towards the negative side, it's more and more negative. It's decreasing faster and faster because it's a parabola, right? Parabolas, like as we go away from the vertex, it gets steeper and steeper, right? It's like a U shape. And for that reason, well, what it looks like is as we go towards the negative side from 0, our slope becomes more and more negative. So we draw something like this, and then it becomes 0 at point 1. So slope, as we go from 1 towards the negative side, it's become more and more negative. It becomes 0 at point 1, right? You see a flat tangent line. And then from 1 to positive infinity, it's become more and more positive. Now, it might be confusing why I drew a straight line curve for the derivative function. And for that, just recall that the parabolas are defined by like the leading term being an x squared, right? And if we were to apply the original definitions of derivative, you'd see that in the end we'd get some equation that would have the leading term in x, and it would be a linear equation. Now the exact equation doesn't matter, but we know that the leading power will be 1. And so we'll draw out a line like this. That's why I drew a straight line. Yeah, so hopefully these examples sort of helped. And yeah, that's basically it for relating a function and its derivatives.